So what we're going to go through here would be your reduction and oxidation reagents. So we'll start off with our reduction reagent summary. Okay, and one of the things that we want to look at is the reduction, or ways we could look at it to try and identify if a reduction or oxidation reagent was used. A reduction involves the reduction of electronegative bonds. Very typically this refers to oxygen. So we could be saying that we decrease the number of bonds to oxygen. This can also be seen as an increase in the number of hydrogen bonds. So as our general example that we've seen in the past from first semester, we take a pi bond, so the second bond of a structure. We could react it in the presence of hydrogen gas and some kind of metal catalyst, typically platinum and palladium, but you'll sometimes see nickel. And the result, we add hydrogen across the double bond, okay? Which then means we've done an addition reaction. It is very specifically a reduction addition reaction. We could reference the electronegative bonds, and that's not super obvious in this case. However, we do see an increase in the number of bonds to hydrogen in this case. For those of you missing out on the what the electronegative bond are, we are technically losing an electronegative atom if we started with an alkene. We'll leave that for our first quiz question. So one of the issues within this reaction is, while it is super common and useful, it's not selective. That means if I had, say, several functional groups in my structure, that I'd have a problem because I couldn't select which one of those to target. Since they're all pi bonds, hydrogen and platinum with this catalyst will likely reduce them to at least some extent. So it's not very selective. Another interesting feature of it is that it will be forced to add in a cis fashion across the double bond, which is a feature of the catalyst being used. So one of the things we might do is try and come up with a more selective catalyst. So in this case, if we start with an alkyne, so now we're getting specifics, we're looking at a functional group, or a different functional group, we can add hydrogen, still cis across the double bond, or across the pi bond, excuse me, but we have to use some kind of poisoned catalyst. So something is in there messing with its dynamics or its functionality so that the hydrogen can't add a second time and we end up not reacting with alkenes, which is kind of neat. Okay, then the next part of it would be, okay, well, I can now specifically add to alkynes, but again, I'm now forced in this cis conformation and it's not particularly easy to adjust out of that. Can I get a trans product? Well, sure enough, yes, we can get a trans product with a new reducing agent. And I would argue this is the tricky one because the active reagent is really sodium metal, okay? Not sodium hydride or sodium ion, sodium metal is the real crux of this reduction, which is interesting because it doesn't have hydrogen. But what it does is it helps donate electrons onto the carbons to make carbanions. The carbanions can react with hydrogen from the solvent, okay? Which then means we go through an intermediate, which will force the trans product, which is kind of neat. Okay. After that, as you might guess, we'd move into our polar pi bonds, kind of our carbonyls. And there's a variety of reducing agents. Notice that these reducing agents are a little bit more spectacular, say, than the standard ones. And that is because we end up removing altogether the oxygen. If we'd gone through and done just a standard H2 and platinum, I don't know why I wrote that, let's do platinum. The result is that we would add hydrogen to both locations, okay, and I'd still have the oxygen present. Notice that with these three sets of reagents, the oxygen is completely removed from the structure and replaced with hydrogen. Okay. The differences between these mechanisms, notice that we've got acids in some of them, we have a strong base in others. So depending on the rest of our structural features, if there's, say, a basic functional group, adding an acidic system is probably not going to be the best idea because the acids will react, or the acid will react with the base. So we want to vary our reducing agent depending on the conditions we're looking at. So our exact kind of mechanistic detail, our hydrogenation, not really a lot of information I can add here. The one big question that would come out of this is, why do we even need a metal? Okay, we've seen these types of addition reactions before where we used bromine. Okay, and bromine didn't need a metal. Why does hydrogen need a metal to react? In this whole process, the metal surface, and so our textbook has done a pretty decent job of drawing this. We've got the metal surface, and the hydrogen gas will adsorb to the surface and kind of separate across the surface of the platinum. Our alkene, or our pi bond, any pi bond, with those electrons can coordinate to that same surface. Once it's attached to the surface, that's when the hydrogens, or the hydrides, on the metal surface can coordinate to our carbons, and they will coordinate in such fashion that we end up putting the hydrogens on the same side of the structure. Okay, so it's just a feature of how that compound gets released from the platinum surface. Once there's no more pi bonds, there's nothing to cause it to adsorb to the surface, and we no longer get our reduction. Okay? And that's why any pi bond can potentially react under these circumstances, because it's really just a pi bond coordination to the metal surface. So we can see an alkyne. Notice that we'll typically have to add excess. Okay, you may not see excess written there. Even if it's not written there, you should draw the fully reduced system. Notice in this case we're using a nickel catalyst instead of the platinum or palladium. The exact details on the platinum or palladium are not important for the scope of this class, but if you were to move into synthesis, do become kind of important. Our poisoned catalyst, it's just our platinum palladium catalyst that has been treated to prevent the adsorption of pi bonds. Okay, this makes it a slower reaction and a lot more controlled. We can then get better results. A specific example of this poison catalyst is something known as Lindlar's catalyst. So you may see it named as opposed to actually drawn out as the reagents. It is specifically palladium metal treated with calcium carbonate and a small amount of quinoline. Just as a guess, the quinoline might adsorb to the surface along with potentially the carbonate, maybe. And those are going to help block some of the sites of reactivity, maybe preventing an alkene from coordinating, whereas an alkyne, being longer and straighter, has a higher likelihood of adsorbing to the surface. If it adsorbs to the surface, the hydrogen can react, and we now have our reduction. And again, the alkene would then have to absorb to the surface, and probably because of some kind of steric effect, blocking either by the quinoline or the carbonate, that can't happen, and we're left with just the alkene. And this can happen under a variety of circumstances. Notice in that first example, we see reference to just Lindlar's catalyst, and in the second example, we see reference to palladium. Okay, so the hydrogen and palladium should immediately say, okay, we're doing a full reduction. We should go all the way to the alkane. Why you should pause is because you're saying something else added. If that something else is added, take it to the alkene, make it cis, you're done. Okay? You could draw parallels, just realize if something else is there, you're probably going to the alkene. What about the trans product? Oh, well, so much for that big surprise. We can't add hydrogen or H2 as a trans formation. Because hydrogen is so small, as we saw in the quiz question, the platinum surface is really required to kind of get it there. Okay. Further, because it's so small, once we've picked up one hydrogen, the other hydrogen does not have the ability to go around to the other side of the surface or the other side of our substrate to attach. That's just physically not possible. Okay, so when using hydrogen gas, we have to get the cis product. So how can we get the trans? Okay, well, this is where I said we bring in sodium metal and ammonia. The sodium metal will react by donating a single electron. That single electron donation causes the formation of a radical and an anion, okay, roughly equivalent to, say, the Grignard. It's not the Grignard, so don't call it that, okay, but it's kind of like that in that we have a carbanion. That is now stupidly basic, and it can deprotonate the solvent of our ammonia. Okay, that can happen a second time, and we've got our full reduction. The sodium won't react with the alkene. We're left with our final product. Okay, so nasty little mechanism. Don't stress on it, but it is there. You should be able to do it. Your textbook goes through and shows some pretty neat tables of listing all these possible functional groups and how hydrogen, catalytic hydrogenation, so the addition of hydrogen, can be done. Notice that they've changed the metal, they've changed temperatures, they've changed pressures in pretty much all of these. Okay? And you might be able to go through and draw some parallels as to why they're going through and making those adjustments. I would argue that's neither here nor there. Maybe we'll talk about it in a lecture if we get a chance. Just realize if you are trying to specifically reduce an aldehyde versus a ketone, the conditions will change. They aren't going to change enough for you to be tested on it as a separate condition. So metal, hydrogen gas, you're good to go. So yeah, that's what's written there. In all of these conditions, what remains of our starting pi bond? Okay, so we did already address this, but let's go ahead and ask it again. In all of these reductions, what remains of the starting polar pi bond? Removing functional groups. So this is where we can bring in those three new reagents. You get your Wolff-Kishner reduction. I would argue almost one of my favorites, or least favorites, because it was a reduction I could never get to work in the lab on at least a particular compound I was working with. But theoretically it works cleanly and beautifully. So we're going to take our starting polar pi bond, and we're going to react it in the presence of KOH, a strong base, and in the presence of hydrazine. Okay, I'm going to leave that one kind of open as for you to figure out what that one's going to act as. Okay, so as we should do with all reactions, take a minute here. How does this reaction work? Do you see any obvious first steps that are possibles for this reaction to go? Believe it or not, you're probably going to want to jump into your second or third option to see how this works. So take a minute, write down what you see. Okay, now that we've got that set, let's go ahead and take a brief examination of this. With a strong base, we might think that it's going to immediately get involved. Okay, well, there's not very many places it can get involved. It can't deprotonate the nitrogen to any real strong extent, so that's not really going to be a good option. And let me rethink that for a moment. Nope, not going to deprotonate that. It could theoretically deprotonate one of these hydrogens, but then all that ends up doing is making this a nucleophile. Okay, well, and that's questionable because if we look at the rest of our reagents, we don't have an electrophile. Okay, so what does this species do? So maybe the base is kind of a side thing. So what does our hydrazine have access to? Okay, well, it's a base as well. It's not as strong a base as the KOH, so we can ignore the base, but it's also a nucleophile. Okay, well, if it's a nucleophile, then that would mean the other species has to be an electrophile. So do we have an electrophilic site in that starting carbonyl compound? Well, yeah, we do. Okay, that carbonyl carbon is electrophilic, which then means we could have our hydrazine come in and attack, and we would end up with a protonated, sorry, my pen's not quite reading right, a fully charged nitrogen, and then an H2. Well, that now being really, really acidic, what does our KOH come in and do? Our KOH can immediately deprotonate that, and we would end up at roughly the equivalent of an acetal. Okay, so as I frantically try and draw this all in, and we might say, well, then where can it go? Aren't we kind of stalled there? Yeah, arguably we are. Okay, so what else gives us a hint that we might be able to do more? Okay, well, that do more, unfortunately, is kind of in that delta symbol. We're given this reaction a significant amount of heat, a little bit of time to go through and process. The nitrogen is still nucleophilic. It can attack a second time, kicking out hydroxide as a leaving group. And we would end up with, again, another polar pi bond. And I may be losing carbons here, so if you catch that, please feel free to shout out. Eventually, maybe I'll hear you. So we end up with another polar pi bond, another acidic hydrogen, which is really bad, so we can have our base come in and pull that off. And we could end up with kind of our imine structure, which hopefully by the time you're officially responsible for watching this video, you'll know what an imine is. Okay, and so, okay, well, now what? Isn't that completely done? Yes and no. So what ends up happening now has to be one of the less obvious things on the planet. With that hydroxide being a strong base, it can deprotonate that nitrogen, which then means those electrons can swing into the other nitrogen, which then means these electrons can come out and pull the hydrogen off of water. Well, if that happens, what do we get? So we've got our nitrogen now connected to our carbon only via a single bond, because the electrons came out as to pick up the hydrogen. Okay, and those electrons had to go towards the carbon, not towards the nitrogen, because we formed a pi bond with the other nitrogen. Okay, and we have one hydrogen left over, and we'd have something along those lines. Okay, well, that's still not a final answer, so what happens? This is where hydroxide can come in again, and this I will leave you to go through and solve the rest of the way out on this. Okay, so see what you can come up with. Realize there are some important resonance structures that we could have used instead of going through the mechanism. Could have looked at a resonance structure for this guy. Okay, and we'll see that there's a really big driving force for this reaction in the formation of that nitrogen gas. It is that triple bond that is now incredibly stable that really drives this whole reaction to completion. So we may be doing a bunch of weird kind of steps in between that are like, well, I don't really like those, but the very last step of the formation of the nitrogen gas is now so incredibly exothermic, okay, that we're seeing a huge favoring for the fully reduced structure. So, the Wolff-Kishner reduction, while it is useful, needs to be avoided if our functional group, or if we have a functional group in the structure that is susceptible to basic conditions or with good nucleophiles. Why? Well, because we have a good nucleophile and we have a strong base. Okay, so if there's anything else in the structure that is reactive, we need to avoid those for that reason, or avoid this reduction for that reason. So we could try a different one. We could try the Clemmensen reduction. And the Clemmensen reduction, if you thought the Wolff-Kishner was weird, the Clemmensen is like freaking nightmarish in comparison. One of the things that I found kind of irritating with this is that there are a variety of different metals that can be involved here. I've seen iron, I've seen tin. They're all using slightly different mechanisms and slightly different conditions under why and when you can do it. So I've kind of gotten to the point of if I see a metal and acid, I'm doing some kind of reduction to a carbonyl. Okay, kind of irritating, but that's the way it works. If we think back to the mechanism idea, we've got kind of a bizarre one going on here. We're going to do an umpolung, much like we did actually for the Wolff-Kishner. Okay, we need to get those red hydrogens attached to that carbon. Okay, that's what they're showing in this reaction. But then that means that carbon has to be negatively charged because the hydrogens are positively charged. Okay, well, this is largely going to come back to the zinc or whatever metal we've got. It has electrons. Those electrons do a nucleophilic attack. Okay, we can protonate. Whoops, should have protonated first. And we can end up with something along these lines. Okay. That zinc structure can then form a bond with a chloride and become positively charged. I then have a negative carbon. That negative carbon can go out and pick out hydrogens from the solvent. It's not a particularly fun mechanism to draw out, so I'm not going to deal with it. But we do end up doing kind of a switch in the reactivity of our carbon. So it's kind of neat for that. Just be aware of it. Yeah, unfortunately that's all I'm going to say with that one. It should be avoided if there's a functional group present that is susceptible to acidic conditions. Okay, so in the previous case, we had basic conditions being a problem. Here we have acidic conditions being a problem because, well, we're using a strong acid to force this reaction to go. Without this strong acid, the reaction kind of fails. Okay, so we need it. And the last one is a Raney-Nickel reduction. This was developed by Murray Raney. It is in 2 steps. So we would take our carbonyl compound and we would react it first with this dithiol compound in the presence of an acid, and we would follow that up with a reaction with Raney-Nickel and hydrogen gas. So the sulfur helps kind of change the structure so that it will react with hydrogen gas and through our nickel catalyst place the hydrogens on. So the only part of this mechanism that you should really have any real knowledge on would be this very first step. Okay, so take a minute, think about it, see if you can come up with an idea to predict what we would expect to see in that magic little box. And with that, hopefully I can push my button. Well, I'm going to try and push it again. Oh shoot, that didn't work. So give me a second here and I'm going to draw it. So the result is that we form what is effectively a cyclic acetal, except for it to be an acetal, those sulfurs would have to be oxygens. So it's known as a thioacetal because we're using those sulfurs. The sulfur chemistry will react with the nickels, probably something to do with the high polarizability of the sulfur because it is so big. As a general rule now for this reduction, it is a reagent that requires a nucleophilic thiol. So if there's a reagent that reacts with nucleophiles, or a part of our structure, sorry, that reacts with nucleophiles, it will be kind of problematic in that case. So we do have to be a little bit cautious on choosing it. The other issue is that we're using hydrogen and a metal catalyst at the very end. So if, say, we had an alkene or an alkyne, well, the Raney-Nickel is going to react with that. Okay, so we have to be very, very careful about the other functional groups present. And I can't remember. Oh, well, we could take a look at this. Synthesis of propylbenzene. Okay, so we'll turn this into a quiz question. See what you can come up with for the synthesis. 8 or fewer carbons is a requirement for your starting. Okay, but you can use any carbon source other than that. And then I forgot the other half of this video is going to be looking at oxidation, which is ultimately the reversal of our reduction. So I put up a couple examples here that we could look at, starting at the alkane and going to an alkene. We should immediately say, well, that is a reversal, but that's also a reversal we don't know how to do. Because we could say it's an elimination, the formation of a pi bond, but there's no leaving group. Okay? With no leaving group in our structure, that's not going to work out so hot. Okay, so we don't have a clean ability to go from the alkane to the alkene. First, we'd have to go through a radical substitution. After we've done the radical substitution, we could follow that with our elimination. So there is no nice reagent to just take you straight there. With the next two reagents, though, with the next one, we're starting with the potential for a leaving group. So that one we could do maybe as a straight elimination. Okay, because it is an oxidation, it has special conditions. So we'll have to talk about what those conditions are for that. And then the last one, again, an alkane. The alkane's not going to go on its own. We have to do the radical substitution, and then we could try and do some planning from there. Probably actually a normal substitution to get the oxygen on, and then we could do an oxidation reaction. Okay, so these are a lot trickier because we need something to mitigate the transfer of electrons, and that's not easy. Okay, so let's take a look at the middle one, because that's going to be the more important one, because that's going to be the one we can do with a single reagent. We want to identify the pieces that were changed or removed. Well, hopefully you can see we remove a hydrogen and a hydrogen, which is a bit odd because those should both come off as positive charges, which would then mean we have a negative carbon and a negative oxygen. I have too many electrons to make the pi bond. So something weird is going on here. Something has to kind of polarize either the carbon or the oxygen to take electrons away from the structure. And that's kind of a bizarre reagent. Before we get into that, our overall idea, we can start with a primary alcohol, and if we oxidize it once, we remove one set of hydrogen, one set of H2, we could end at the aldehyde, but there is still another hydrogen to be removed, so I could remove another hydrogen, and I could take that all the way down to the carboxylic acid. Okay. If I started with a secondary alcohol, I can remove my hydrogen and I'd end up with a ketone. But now there's no more hydrogens to remove from our reactive carbon, the one where the oxygen's bound, and so I can't do any further oxidation, okay? At least cleanly. So it's done. And if I started with a tertiary alcohol, again, no hydrogens to remove, I can't do any more oxidation. It stalls right there. Okay? So we need that hydrogen to be able to do the oxidation. Okay? So, the reagents. There's really only two, though unfortunately one of those shows up in a variety of stinking forms. Okay, we have chromic acid, which can be called Jones reagent, which can be shown as H2CrO4, which can be shown as K2Cr2O7, H2SO4. It could be written out as dichromate. It could be written out as chromic acid. I mean, there's just a stupid number of ways that that reagent can get presented. Okay. Any way you dice it, though, it is a stupidly strong oxidizing agent. Which means if I start with a primary alcohol, what happens? I go all the way down to the carboxylic acid. Okay? I do not stop at the aldehyde. Okay? The secondary alcohol will stop at the ketone, and it really didn't have much of a choice because, well, that's where that one stops. The other reagent that we can use is what's known as pyridinium chlorochromate, or more commonly referred to as PCC. I like to think of this as politically correct chromic acid because politically correct humor is always boring and not very exciting. So it's a little bit of the milder version of the crude and harsh humor. Okay, why is that important? Well, when it's a secondary alcohol, it's not important. Okay, it goes straight to the ketone, and we don't really have anything to oxidize further beyond that or less than that, so it stops there. Okay, but the primary alcohol is going to be where PCC sets itself apart. It will stop at the aldehyde. It will not go to form the carboxylic acid, okay, which is kind of a neat feature of PCC. The chromic acid, I just want to kind of address this. There's tons of different ways that this can be shown. Okay, one of the things that you'll notice typically when looking at the chromic acid part, or only when looking at the chromic acid part, you will also see mention of H2O in some form or another. It is actually critical to chromic acid doing its job. Okay, so water needs to be there. In PCC, you should see no water present, because if water is present, everything kind of goes out the window. So, why the big difference? Well, I actually kind of just addressed it. In chromic acid, we have water, and again, stupid slides. In PCC, we have pyridinium. This is pyridinium. It is the acid salt of pyridine, which is our solvent. Much the same as water acts as a solvent. Okay? But why use pyridine instead of water? Well, what is the extra feature that water has that pyridine is not quite as good at? Water is a really good nucleophile. That nucleophilic characteristic is what sets these two reagents apart. Chromic acid will oxidize like crazy because water is present. Okay? Because if we look at the reagents, PCC is the exact same thing as chromic acid, except no water. It has pyridine. That's why it's called pyridinium chlorochromate. Okay? So, if we look at an approximate mechanism for this, our alcohol will act as a nucleophile with our chromic acid species. Okay, the chromic acid species is highly electrophilic because of all of the electronegative oxygens attached to it. Okay, and what will end up happening is, under acidic enough conditions, we'll kick out water as a leaving group, and we will have the chromate ester. Okay, it's a chromate ester because we have a carbonyl and an oxygen bond with the chromium there. That chromate ester is the clutch of our oxidation step. Okay, and what happens is anything remotely basic in solution, and this is where you might challenge me, because if we think back to our reagents, everything's stupidly acidic in solution. Okay, but there is water. There is also more alcohol present in solution. Both of those are basic enough to remove a hydrogen. That then puts too many electrons on our carbon, So we go to forming the pi bond. The oxygen then has too many electrons, and here's where we make our chromium happy. The chromium has now accepted electrons permanently. It's gone from being a +6 down to, I may be getting it wrong, but I think it's a +4. So it's accepted those electrons. It's now significantly happier as far as its oxidation state because it's becoming more neutral. And the result is that we form an aldehyde. Both mechanisms go through and produce this aldehyde structure. The question then becomes, why does chromic acid and not PCC continue to react? Okay, well, that again goes back to what we addressed. Water is a nucleophile. What happens when I put water near an aldehyde? There it is. We form the acetal. The acetal becomes useful because now what do I have? Well, now I have a nucleophilic oxygen that can attack a second chromium molecule. And I can now initiate the cascade of events just like I did before, going through ultimately, let's see, did I actually show it? No. Ultimately, starting the cascade of events that we just saw, taking us down all the way to the carboxylic acid. So if water is present, we get the carboxylic acid. Chromic acid almost always has water present unless it very specifically says PCC or the presence of pyridine, PYR. Okay? Your textbook had some nice kind of pictures on it, so you can use those instead of my ugly ones to see the chromate ester and how your hydrogen is removed to form your carbonyl. So here's your big summary of everything. What I try to do is put it all nice and neatly on one slide so you can see your primary, your secondary, and your tertiary alcohols. So we're starting up here at the primary because we're saying the R groups. Only one of them is a carbon, the other two are hydrogens. Well, that would be a primary alcohol. So we have our primary alcohol, our secondary alcohol, what we would expect to get, the tertiary alcohol, and then I invert it so that the tertiary can overlap for our PCCs. Okay? The big key difference that you really, really need to remember is that one. If you want to make the aldehyde, you must use PCC. If you don't need to make the aldehyde, then it really doesn't matter what reagent or which of those two you use. They'll both end up at the exact same spot. Other oxidizing agents, we have seen permanganate show up. And if we compare structurally permanganate to chromic acid, you should see that they are very, very similar. And they are. They have similar chemistries. They have similar reactivities. Okay? Permanganate made carbonyls from nonpolar pi bonds. Should it also work on alcohols? Well, if it was a super strong oxidizing agent, we might expect so. And sure enough, it does. So permanganate can be used to oxidize our alcohols down to ketones or carboxylic acids. Again, carboxylic acids. Why? Permanganate is a stronger oxidizing agent, stronger than our chromic acid. Okay. There's another big issue with our chromic acid, is that even though it does work and it does fully oxidize, okay, what do we kind of expect out of this? Okay, so number one, we get our carboxylic acid. I guess I should have written this out. Yeah, well, too late now, I already said it. Carboxylic acid. For a secondary alcohol, we'd end up with what functional group? Hopefully you said a ketone. And then for the tertiary alcohol, we get nothing. Okay, there's nothing for it to oxidize. Okay, so it does a pretty good job of oxidizing things down. However, what is our issue with selectivity? Okay, well, chromic acid only works on our alcohols. Permanganate also worked on alkenes. Okay, so what does that mean? Chromic acid is more selective than permanganate. So we would typically want to use chromic acid over permanganate in that respect, because we get a more selective or more careful reagent. Are there other things that we should be concerned about? I don't know, say like safety or cost. Okay, well, it turns out chromic acid is highly, highly toxic. If you've heard about Erin Brockovich and what she was working against, the chemical that whole movie and book was based around was chromium-6 ion, which happens to be the oxidation state of chromic acid. Okay? So permanganate is a little bit safer. It is also less expensive than chromic acid, probably due to that toxicity concern. Okay? So it's a balance. You kind of got to decide which way you want to go with it. And with that, I think we are done. So thanks for watching.